This is the small signal equivalent of the common source amplifier. It has these two AC coupling capacitors C1 and C2. Earlier we did all our analysis assuming that C1 and C2 are large. Okay. If they are infinitely large, they do behave like short circuits. Now we will see exactly how large they have to be. Okay. In order to analyze a circuit which has capacitors and inductors, we need to do sinusoidal steady state analysis. We will assume that the input Vs is a sinusoid at a frequency omega, okay, some omega. And we know that while doing sinusoidal analysis, we represent all voltages and currents by phasors. That is what I do here. This is the phasor corresponding to the input voltage. Okay. And we have Rs. The C1 will be an impedance 1 by j omega C1, and this voltage here Vgs, again I will represent it as a phasor, that is Vgs, and the output voltage here is Vo, and we will also need this voltage later, and I will call that Vd. Okay. So, that is the incremental drain voltage phasor, or the voltage between drain and source. Okay. Now, I will assume that you are all familiar with sinusoidal steady state analysis. If not, please go back to basic electrical circuits and brush up your basics. Okay. Now, this current source of course is Gm times Vgs, which is the phasor. Okay. Now, Vs gets divided between these impedances and R1 parallel R2 to give you Vgs, and Vgs gives you V naught. Okay. So, I will evaluate these two expressions separately, essentially Vgs by Vs and Vo by Vgs, and I could combine the whole thing to give me Vo by Vs. If I multiply the two, I will get Vo by Vs. I do not want to write lengthy expressions, so that is why I stick to this. Okay. So, if you do the analysis correctly, you will see that Vgs by Vs, basically the fraction of Vs that appears as Vgs, this is equal to R1 parallel R2 divided by R1 parallel R2 plus Rs plus 1 by j omega C1, which can be written as j omega C1 R1 parallel R2 divided by 1 plus j omega C1 R1 parallel R2 plus Rs. Okay. Now, what do we mean by C1 is very large? Basically, it should behave like a short circuit. We know that if it did behave like a short circuit, Vgs by Vs will simply be the ratio of these resistors R1 parallel R2 divided by R1 parallel R2 plus Rs. Okay. And here we can very easily see that if this part here, if omega C1 times R1 parallel R2 plus Rs is much more than 1, then we can simply neglect this 1 in the denominator, and this j omega C1 will cancel out, and this expression will reduce to this R1 parallel R2 divided by R1 parallel R2 plus Rs, which is the resistive divider expression. Okay. So, this is the criterion for choosing the capacitor, or C1 must be much greater than 1 by omega R1 parallel R2 plus Rs and so on. Or in other words, if I write it in terms of the reactance of the capacitor, I will have the reactance of the capacitor 1 by omega C1 much smaller than R1 parallel R2 plus Rs. Okay. So, this is the criterion for C1. And what does it mean in terms of the circuit? If I reduce this Vs to 0, okay, That is, when the input to the circuit is nulled, this is the circuit we have. And you simply see that RS plus R2 parallel R1, which you see in this expression, is the resistance that appears across C1. Okay. Now, again, if you recall basic electrical circuits, the way you evaluate time constants in a first order system is by looking at the resistance that appears across a capacitor. Okay. So, that is exactly what we are doing here. Now, one more point I have to quickly mention is that this is a second order system, but there are two separate first order systems which are decoupled. Okay. So, it is correct to treat these as two separate first order systems. So, this is a first order system, and all you have to do is to find out the resistance that appears across the capacitor and make sure that the capacitive reactance is much smaller than that resistance. Okay. Or in other words, another way of saying that is to make sure that the time constant is much more than the reciprocal of the frequency. And when I say frequency here, this omega is in radians per second. So, please keep that in mind. Okay. So, all these criteria mean the same thing. Okay. So, you should be able to relate this to what you learned in basic electrical circuits. So, that is how you choose C1. You just have to make sure that the reactance of that capacitor C1 is much smaller than Rs plus R1 parallel R2. Then it behaves like a short circuit. That is what we mean by a large enough capacitor. Okay. In practice, what is done is we have an inequality, that is C1 much greater than 1 by omega times R1 parallel R2 plus Rs. Okay. So, what is the actual value that you choose for C1? So, let us say you evaluate this expression and this comes out to 10 nanofarads. Okay. Now, what should be C1? If it is 1 microfarad, it is more than this. If it is 1 millifarad, it is also much more than this. Okay. But of course, you do not go crazy like that. Typically, if you take C1 to be, let us say 10 times this constraint, okay, 10 times 10 nanofarad equals 100 nanofarad, that is good enough. Okay. Or you can make it a little more, but you do not have to make it like 1000 times or something like that. Okay.